Okay, we are now ready for chapter 4.4. The topic of this chapter is extreme values. We will first give the subtopic of maximum minimum values. Let me give the following introduction. Let f be a function of a single variable like y is equal to f of x, and let this c number be a point in the domain of f. Let me show it by this notation. Then we say the following: then f is said to have. So here are the types of maximum and minimum values that f may have. The first one, let me state it in the following way. We have let's say an absolute, so somehow we call it, you can also see in some book, global maximum, let's say at point C, if this is the definition of absolute maximum of f at point C, if f of c is greater than f of x for all x in the domain of f. So similarly, we can define an absolute global minimum at point C if, now we have reverse, f of c is smaller than f of x, because it must be, in order to be minimum, it must be smaller than all of the other values for all x in the domain of f. So next one, we may also have a local maximum at point C if, so in this case we have another version of the first definition, maximum, but it is just locally, so we will show it in the following way: f of c is greater than f of x for all x in a neighborhood of c let's say neighborhood of c which are indeed in domain of f. And the last one, we may have a local minimum at point C. Again, if in that case we have just reverse of it, f of c is smaller or equal to f of x. Again, we have for all x in a neighborhood of c in domain of c. Here we in a neighborhood of c means, so you are checking if this is point c, you are just looking at the around the point of c. So this c is in the domain of f, and you check the maximum minimum of f around that point c. So in that case, we say these points are maximum and minimum values of the, or extreme values, let me write it, these maximum minimum values, which means the above one, the absolute global, absolute minimum, local maximum or local minimum points. These maximum minimum values are extreme values of f. Okay, this is what we have as a simple definition. Okay, we may have, maybe, let me show it in a graph. So if we have the following type of graph, let's say this is y-axis, this is x-axis. So let me just introduce a simple graph of f in that way. and let's say this is somehow a point. Maybe it's better to continue this graph a little bit. Okay, let's say x. So let me say this point is B, this point is A. Okay, somewhere here, as you see, you have point here is a maximum, but a local maximum. Here you may have a minimum point. So we call the following way. So this point, so if you are in the interval, so since here y is equal to f of x is continuous on AB, obviously, and here we call that point as absolute maximum, because when you compare the whole interval, this is the minimum, absolute minimum, this is absolute minimum when you compare the whole interval, and that point is our absolute maximum. Here you see, here at that point you have a local minimum, and that point you have a local maximum. Maybe you can understand the difference between locally and the local maximum and the absolute maximum, comparing with each other. We may have a simple example. Let us consider f of x as cosine x. Again, if I sketch a simple graph for cosine, so it is a periodic function. So for 0 it is 1. Then let me sketch it in the following way. It is periodically continuous up to infinity. So here we have, so this is 1, this is 0, so let me rewrite again. This is 0.1, 0 at pi over 2 it is 0. Somewhere here it is pi, and it gets the number -1, and so on. Okay, it is periodically, it changes periodically in the interval between -1 and 1. It oscillates, and here you can directly have this conclusion: absolute maximum for f is 1, because it cannot take any other value than 1. But moreover, you can also have local maximum for f is also 1, and absolute minimum for f is -1. At the same time, local minimum for f is also -1. In that example, you see they coincide. Another simple example, take f of x as x squared. So if I sketch again another figure, you are already familiar with this graph. We have again xy, and it is an even function passing to 0. So you can sketch better. Okay, it is not a good sketch, but let us say this is y is equal to x squared, or f of x is equal to x squared. So as you see, it has a minimum at that point, obviously at point 0. We have f of 0 equal to 0 for that example. F of 0, comparing the other values, all of the values of x, it is f of 0 is a local minimum, but at the same time it is an absolute minimum, because we have no other value than that. And you can also observe easily that f of x, f has no absolute max, no absolute min. This is also directly from the figure, you can check. So there are some methods to see, to understand if you have local minimum and local maximum, but we will check them in the following. Okay, Okay, another, maybe we can terminate by that example, and we will have another definition. F of x be given as x power 3. Now you will understand better the idea, I guess. So if you consider the graph of f again, it is an odd function passing through 0, y is equal to x power 3. And as you see, we have no absolute or local max, no absolute local mean, because it is an increasing function between minus infinity and infinity. Okay, so let me write the following. Extreme value theorem. This theorem is important. Extreme value theorem. Okay, let us state the theorem. If f is continuous on a closed and finite interval. So instead of that, you can directly write, if you know already what is the meaning of closed and what is the meaning of finite interval, instead of writing f is continuous on a closed and finite interval, you can directly say f is continuous on AB. Okay, here we have a closed interval. Notation is important. Don't write as a parenthesis. This is these are brackets. Okay, we have closed interval. Then f must have, so this is a strict condition, an absolute maximum and at least one. Okay, we have at least one. F must have, maybe we can erase this. F must have absolute maximum and absolute minimum value or values on AB. They may also coincide in that case. And the following, again, we have a corollary of that one, the theorem. Let me say Fermat's. So you can check for proof, you can check your book. I will not give proof. Fermat's theorem. So it is important to understand the idea. Whenever you have an example with the closed interval, you can say directly by extreme value theorem, and we use the following abbreviation, EVT, extreme value theorem. There must exist absolute maximum and minimum values. So this theorem says if f has a local maximum or local minimum at a point C, and moreover, and if f prime C exists. Okay, we have two conditions. You have either local maximum or minimum at point C, and moreover f prime C exists. Of course, f is differentiable. Let me also write it in the parentheses. If f is differentiable, of course. Let's see. Otherwise, you cannot talk about C. Okay, this is obvious, but let us state it again. Then f prime C equal to 0. So this is a strict condition. As you see, we have in these two cases implies f prime C equal to 0. Let me check if I have any example for this simple fact. Maybe we can have a note before the example. The reverse of Fermat's theorem is not always true. What is the meaning of reverse? Let us see in the following. Let us observe that we have f prime C equal to 0, but f do not have what was the case? Let me read again the theorem. F prime C equal to 0, and then we will have f do not have a local maximum or local minimum. Then we will have an example, f of x, use black color, f of x is x power 3. We did already this example. We had the following graph or function, no max, no min. We already stated in the previous page. Let me check f prime. F prime x is equal to 3x squared, and as you see, f prime exists and f prime 0 equal to 0. However, f has no local max or min. So this is the statement that we have written here, note in the note. So we have the reverse case, f prime is 0, f is differentiable, but it has no local maximum and local minimum. And moreover, I will give you another example. Let us check the example f of x, which is equal to absolute value x. Again, if you sketch, maybe it may be better to understand for that example. And the graph of function absolute value we did already in the first week, if you remember. Okay, we have the following two lines. So this is y is equal to absolute value x, this is 0, and in that case this is also a good example. In that way, f has a local minimum at point x is 0, but it is not differentiable. It is not differentiable at x is 0. Why? So maybe this is a good question for you if you think about that point. At that point we already studied differentiability, but you see that we have a sharp point here. So here you have this sharp point. When you apply 0 from left side, the slope will be -1. When you apply approach 0 from right side, this is 0. Sorry, let me write it again. I guess you did already in differentiability part, but let me say here. When you approach from 0 from right side, the slope is 1. 0 from left side, slope is -1. So it means there are two different limits, so it is not differentiable. Derivative does not exist at point 0. Okay, we can write the following remark. A function f can have or may have extreme values only at points of x of 3 spatial types. And we will now study these spatial types of points. In other words, if we have extreme values, one of the 3 points may be our cases. We have not fourth case. So if it is an extreme value, then either 1, 2 or 3 must be satisfied. The first type of points are called critical points. Critical points of f. So these points are the points. These are the points. So let me write without parentheses. Maybe it's better to say. Right here. So let's say C is a critical point of f if f prime c equal to 0. And second type of points are called singular points of f. And for those type of points, we say C is a singular point of f if f prime C does not exist. Does not exist. We can underline this important fact. And the third one, we may have endpoints of f. So for endpoints, you will have you have to consider the domain of f, or if you are given an interval, you check the endpoints of the interval, closed interval. Okay. Let us do examples of this spatial type of points. Example: find the absolute maximum minimum values of f of x, which is given as x times 4 minus x square on the interval -1 and 2. Okay, first of all, for those type of questions, you must first note that you are given a closed interval. This is a closed interval, and f is a continuous function or not. You have to check it. Okay, we have to check if f is continuous or not. First of all, what is the domain of f? We have to check the interval where f is defined. To answer this question, you must check so we have no problem with x. We have to check the square root of x, 4 minus x square. So you must have 4 minus x square greater than or equal to 0 in order to f be defined. So this implies 2 minus x, 2 plus x greater or equal than 0. So then, if we have -2 and 2 here, you will have this is a simple table to see the sign of the function. So since x is minus, we have minus plus minus. It means f is defined. So this is the interval where f is defined. F is defined on the interval -2 and 2. And the question is given where? The question is given -1 and 2. So -1 and 2 is already in the interval -2 and 2. Okay, so we have no problem with the domain. It means f is continuous on the interval -1 and 2, and this interval is closed. So by extreme value theorem, f must have absolute max and minimum on the interval -1 and 2. Okay, if you can observe this simple fact, then you have to search for these points. So this is what we will do in the following. We will check first the critical points. Second one, find f at these critical points. Then the third case, for endpoints, what are the endpoints? We have -1, x is -1, and x is 2. Find the values of f of -1 and f of 2. Then compare 2 and 3, the values of f, to decide which is the maximum and which is the minimum. Okay, we can first start by checking the first case, critical points. For that, you have to answer this question: f prime x. What is f prime x? Derivative of first one times second one, first one. So you apply derivative of x is 1, then plus times the second one. The second derivative x times inside term minus 2x over 2 times 4 minus x squared. And if you arrange the terms, we have 4 minus x squared minus x squared over 4 minus x squared in square root, which gives us 4 minus 2x squared over 4 minus x squared. Okay, let me continue in the other page. So if f prime x equal to 0, this implies 4 minus 2x squared equal to 0, and so we have to have x squared equal to 2. In other words, x is equal to plus or minus square root of 2. So critical points, remember, those points which makes which make f prime equal to 0. Critical points are c1 is square root of 2, c2 is minus square root of 2. But here we have a question. Are those critical points in the interval? Because we are studying in the interval minus 1 and 2. So answer C1, yes, it is in the interval minus 1 and 2. However, C2, which is minus square root of 2, is not in the interval minus 1 and 2. In other words, we ignore C2 as it is not in minus 1 and 2. Okay, we have now one point. Let me take it in the following square. So critical points is finished. So now we have to check now singular points. Do we have singular points? For which points or point f is not defined? You have to look at the denominator. Remember, f prime x was equal to 4 minus 2x squared over 4 minus x squared in the square root. So if f prime is not defined, this implies that 4 minus x squared must be equal to 0. So this implies x is equal to plus or minus 2 are singular points. Again, we ask the question, are those points in the interval minus 1 and 2? We give the following answer. Since x is equal to minus 2 is not in the interval minus 1 and 2, we ignore x is equal to minus 2. Thus, the only singular point is x is equal to 2. We keep that point. Again, we have 2 points now. And what do we have? We have a critical point, a singular point, and check endpoints. X is equal to minus 1 and x is equal to 2. So you see that at the same time x is equal to 2 is a singular point and it is an endpoint. So anyway, we can check the values of f at those points. F of minus 1 is equal to, if you put f of minus 1, we have minus 1 times 4 minus 1, which is equal to minus square root of 3. If you put f of 2, you have 0. Okay, 2 values already we have, that one and then that one, and moreover these are endpoints. Critical points, what was the critical point of us? We had square root of 2. F of square root of 2 is equal to square root of 2 times 4 minus 2, which is again square root of 2. We have this is equal to 2, and moreover singular point already calculated, but let me again calculate it. We have f of 2 equal to 0. Now you make the following comparison between those. These are the values that you have. Then compare these values. Compare these values. What do we have as a conclusion? Obviously, you can say that f has, so this is the maximum one, 2, 0 is the minimum one. F has absolute maximum, because you have to have absolute maximum at x is equal to square root of 2, which has the value 2, and f has absolute minimum at point x is 0, which has the value minus square root of 3. Okay, we have 3 values, so I forgot that one. So we have, this is the minimum, this is the maximum one. But don't confuse the following. The maximum value is 2 and minimum value is minus square root of 2, but maximum value appears at the point square root of 2, minimum value appears at the point x is 0. Do not confuse these points and the values of f. Okay, I have another example. F of x is given as x squared minus x minus 2. This is given on absolute value on the interval minus 3 and 3. Decide or check the extreme values of f on minus square root of 3 and 3. So this is a nice question. If you check previous year exam question, you can find easily absolute value questions where we ask the absolute extreme values of the function. Okay, here we do first the following. F is continuous because f has no value which makes f undefined. F is continuous on R because it is polynomial, let's say. It is polynomial even if it is in the absolute value. So it means f is continuous on the interval minus 3 and 3. Moreover, this interval is closed. Minus 3 and 3 is closed. So it means f must have absolute max and absolute min values on minus 3 and 3 by we can say by extreme value theorem. Okay, let us see what are those values. But first of all, you recall f of x equal to square root of x, or y is equal to square root of x, is not differentiable at x is 0. We did it already. So you remember we had the following form, and at 0 from left and right side we have two different slopes, so we have no differentiability. So you can generalize this fact in the following. You can say the following: f of x, which is given as x squared minus x minus 2, is not differentiable at where? Okay, this is a question. At blah blah. The values where this is 0. Okay, because we have at 0 we have a problem here. So if you rewrite it as x minus 2 x plus 1, obviously you can say is not differentiable at x is equal to 2 and x is equal to minus 1. Please note this example. Okay, this is a nice example. Or you can also sketch the following table for the value minus 1 and 2. If you remember from high school, probably you can say for whenever, so these are the roots of f. Whenever it is, so it is positive, this is plus minus plus, so it is positive here, negative here, positive here. So we can rewrite f of x in the following way. Whenever it is positive, you have directly, you can get rid of square root. sorry, you can get rid of absolute value, then we have x squared minus x minus 2x is smaller than minus 1 or x is greater than 2. And for negative values, we have to have minus x squared plus x plus 2 whenever x is between minus 1 and 2. This is just to observe the sign of f, the behavior of sign of f in those intervals. Okay, let us, if you consider that function, then you can say f prime of x will be 2x minus 1 whenever x is small equal to than minus 1 or x is greater than 2, and minus 2x plus 1 whenever if x is between 1 and 2. So this is not a necessity, but just see the detail of calculation. So in other words, we can write the following conclusion. Since f is so we have already written that f must have absolute maximum minimum. We have already stated that f is not differentiable at point minus 1, so note that. We can rewrite again. Note that f is not differentiable at x is equal to minus 1 and x is equal to 2. So f minus 1, f prime minus 1 and f prime 2 do not exist. What does it mean? Remember the fact that we have written 3 cases of the spatial points. One of those points were those points was singular point, and at singular points we had f prime does not exist, and here in that case f prime minus 1 and f prime 2, they do not exist, which means the point, so thus x is equal to minus 1 and x is equal to 2 are singular points. Okay, this is the first observation. The other observation, do we have critical points? What about critical points? Because whenever we decide the absolute maximum minimum, we must check all of those critical points. Do we have critical points? You check what? You have to check for critical points, you check f prime x. Whenever it is 0, we have to have critical points. So for both cases, if you check the both partial cases of function f at point 0 for f prime, x will be equal to 1 over 2. X equal to 1 over 2 is the only critical point. Okay, and moreover, what do we check? We have to check endpoints, because we have a closed interval. What are those x points? X is 3 and x is minus 3, and check the values of f at those points. F of 3 is equal to, if you write it, 9 minus 3 minus 2 is equal to 4, and f of minus 3 is equal to 9 plus 3 minus 2, which is 10. Okay, now compare the values. Maybe we can write here f of 1 over 2. What is f of 1 over 2? You can write it and you find 1 over 4 minus 1 over 2 minus 2, which gives us 9 over 4. For singular points, do we have, maybe we can also write here for that one, f of minus 1 is equal to 1 plus 1 minus 2 equal to 0, and for that point f of 2 is equal to 4 minus 2 minus 2 equal to 0. Okay, we have now everything to compare. So these are the singular points. This is my critical point value, and those 2 points are endpoints. Which is the maximum, which is the minimum? You can obviously check that. Absolute maximum value of f is, can you see it? 10. Okay, it's 10, which occurs at x is equal to minus 3. But the important thing here is 10 is important for us. But if the question says at which point f has maximum, value, then you must state x is equal to minus 3. And moreover, let me write the other one. Absolute minimum value of f is, for if you check, we have 0 is the minimum one, is 0, which occurs at 2 points indeed. X is equal to minus 1 and x is equal to 2. Do we have local max, local minimum? So this is not the question. We have maybe, okay, we have just asked in this question, we have by extreme value theorems, we have absolute maximum, absolute minimum, and we found both of those points. State in the following way. Okay. So I guess it is not complicated. Okay, we have another theorem now, the first derivative test. This theorem will help us to decide if we have local maximum and local minimum. In the statement you will see what I mean. Let C be a critical point of a continuous function f. So we have now two cases. A, if f prime changes from positive to negative, it means the sign of f, okay, at point C, then f has a local maximum at C. It is easy if you sketch the table of the of function f in the following form. This is f prime, this is the point C. Here we have, it says from plus to negative. In other words, if you draw the following arrows, this is increasing, decreasing, so you will have a function of this form. You see that we have a maximum at that point. So in other words, here we have local max. It is not difficult to understand if you sketch in this way. It has the following behavior in it. B, if f prime changes from negative, now we have reverse case, negative to positive. At C, then f has a local minimum at C. And this is also obvious. Just again, if you draw a table, this is my f prime, this is point C. It says f is changed from negative to positive. Here it is decreasing, here it is increasing. In other words, we have the following shape. So here we have local minimum. So it has the following figure. So here this you can verify that easily. So this is a kind of minimum. This is a kind of maximum, that point. Locally, of course. We have the third case, C. If f prime does not change sign at C, then we say f has no local max or mean at point C. In other words, again, if f prime is given in the following table, so you have C, and this is always plus plus, so it means it is increasing, so it doesn't give us any local minimum or maximum. Again, we have, if we have f prime and this is point C minus minus, it is decreasing, so no local minimum or maximum for both those cases. No local max or min. Moreover, if we have endpoints, they must also be considered. We must check the values of f at these points. So of course these are in the domain, endpoints in the domain. Let me give you a simple example. F of x is 5 minus 3x squared plus x power 3. Okay, check the local minimum, local maximum points for that function. Check the local min and max of f. It doesn't say in an interval in this question, so you will check it in the whole R. So that's why, for instance, if it is given in an interval, then you can use extreme value theorem for absolute maximum, absolute minimum, but probably in that question we have not absolute maximum and minimum, and local maximum and local minimum can be observed easily. So what was our first derivative test? So you apply f prime x, which is minus 6x plus 3x squared. By the way, you can say f is a polynomial and it is continuous. It is continuous on R, everywhere on R, of course. So which value makes f prime equal to 0? If you rewrite it again, minus 3x, 2 minus x. So it means f prime of x is 0 if x is 0 or x is 2. So these are critical points. Let me sketch the table again. You have the point 0 here, 2 here, so you must be able to use this table method. It will be useful for us when we sketch the graphs. We have just one root, and the sign of function is, in that case, the greater one is x squared, so we start by plus, minus, plus, increasing, decreasing, increasing. Conclusion, here you have local max, here we have local min. Okay, by the first derivative test, so we say f has a local max at x is 0 and f of 0 is equal to, if you put 0 in the given function, you have 5, and f has a local minimum at x is 2 and f of 2 is equal to 1. Since f is a polynomial, f has no singular point. You can just check it. You can just state, okay, we have for polynomials, for continuous functions, and since the derivative is defined everywhere, it has no singular point. We have a question. What do we do if we have open intervals? Okay. We did our extreme value theorem whenever we have closed interval. In that example, sorry, in the following statement, we will see how we can deal with this type of problems whenever we have open intervals. Let's say existence of extreme values on open intervals. This is a subsection. Okay, let me write the following statement. So before, let me see if I forgot any example that I have to do. Okay, maybe there is a good example, but it is of that part, maybe we can write it. Okay, let me state this is again a theorem indeed. theorem. If f is continuous on the interval AB, so you now pay attention that AB is an open interval. This is an open interval. And moreover, if limit x to the a from right side f of x is L, limit x to the b from left side of b f of x is M. In other words, you can consider the following: here a, here b, so you have an open interval, and when you apply limit, so you approach b from left side, you approach a from right side. Okay, and here limit, we have limit for those 2 points, and moreover we have the following. Then there are two statements, 2 or 3 statements. Let me write it. Okay, let me write. Fine. If there exists some u in the interval AB such that if f of u is greater than L and f of u is greater than M, for some u in AB, so you have a u in the interval somewhere here, let's say, then f has an absolute maximum on AB if both limits are smaller than the value of u. Second case, if f of u is smaller than L and f of u is smaller than M for some u in AB, then we say then f has, so these values are smaller than the limit values, so it means we have absolute minimum value on AB. Did we have any others? No, we have just those two. Okay, let me write an example how we can deal with, how we can use this theorem. Do I have a good example? Yeah, okay, this is a good example. Example, let f of x be x squared plus 54 over x plus 5 be defined on 0, infinity. So at 0 we have a problem, but then when you have x values are greater than 0, we have no problem. It is continuous everywhere. So that f has an absolute minimum on 0, infinity, and find this value. Okay, we must check, so remember the theorem, so we must check, notice that limit x to the infinity f of x, when you have infinity, the first term will approach the infinity, second one is 0, third one is a constant, so we have infinity, and limit, let me calculate both here, x to 0, because we have to check these points, so a, b points, this is a, this is b, 0 is a, infinity is b. Then we have f of x This is again, we have 0 first one, second one is infinity, third one constant, so we have again infinity. And what do we say? Notice that both are, so this is my L, this is my M in that case. And f of x is smaller than infinity for all x in the interval 0 infinity. If you put any value of x for the function in the function f, you will see that it is a finite number except infinity and 0. Between the infinity and 0, it means for any u, where u is between the interval 0 and infinity, remember the theorem. So here we have infinity, so somewhere here u exists. So for any fu, this fu will be smaller than l and m number. These are infinity. So then by above theorem, by the theorem above, f must have or does have an absolute minimum on the interval 0 infinity. Why minimum? Because we have maximum cannot be maximum, because infinity, we have already infinity. So it is approaching to infinity for endpoints. So you cannot have maximum. You can have minimum if exists. And if in this case the existence is guaranteed, since we have a polynomial. So moreover, how we can see that point? We have f prime of x is equal to 2x minus 54 over x squared plus 0. So you are checking for critical point. Do we have critical points? So then this is equal to, again, 0 implies, if it is equal to 0, then what do we have? 2x is equal to 54 over x squared. This implies x is equal to 3x, x power 3, 27, x is equal to 3. Okay, now we have an idea about function. Here you see that if you draw a simple graph of function f prime, this is the point 3. So at 0 we have infinity, at infinity we have infinity. So whenever, if you check the function, in that case you must pay attention, because the function f of x, indeed f of x is equal to 2x squared minus 54 over x squared. This is my f prime x. So at 0 we have a problem, but the sign of x is positive, so that's why you start by plus, minus. So there is a simple trick here. And then the function will be decreasing, increasing. This means here we have a minimum, local or not. So we already know that this is a local minimum indeed from the statement that we had previously. So let me say, so we have no other case. But remember, recall that extreme values may occur at 1 critical points, 2 singular points, 3 endpoints. Here in that example, endpoints are plus, so these points for 0 and infinity, f tends to infinity. For singular point, there is no singular point. Indeed, 0 is a singular point for f prime. Here we have 0, but again it is infinity. But critical point x is equal to 3. Then conclusion, we can say that f has absolute minimum at point x is 3, and it is equal to, or we can say, and f of 3 is equal to, we can write that the value. If you put in the function, if you put 3, what do we have? We have 9 plus 5, we have 14, plus, if you write 3, let me write, okay, 17 plus 9. Indeed, it is not asked, but let me write it. 9 plus 54 over 3 plus 5, 9 plus 18 plus 5, which gives us 27, 32. Okay, this is our absolute minimum at point 3. I will terminate our lecture by a last example. Let me see if I have no other example. Okay, we have a last example. This is a nice example, that's why I want to solve it. Last example, f of x is given as x times e power minus x squared. There are similar questions in your station. On R is given, first case, find and classify the critical points of f. Second case, does f have any absolute max and min? Okay, we will apply our last theorem as we did in the previous example. F is continuous, first case, continuous on R, but extreme value theorem cannot be used. Why? Because since we have not a closed interval, we have R is equal to what? So let me say, since R is equal to, do we have any statement there? No, it's not given. R is equal to minus infinity plus infinity. So that's why we have open interval. Okay. And what do we have? F prime x is equal to e power minus x squared plus x times minus 2x times e power minus x squared. If you rewrite it in the parentheses of e power minus x squared, we have 1 minus 2x squared. Do we have any mistake here? No. Okay, it's okay. This is multiplication. It is equal to 1 minus 2x squared over e power x squared. If f prime is 0, if f prime x is equal to 0, this implies that x is equal to plus or minus 1 over square root of 2. So these are the critical points. This is the first step. And again I sketch a simple table. Minus 1 over square root of 2 plus 1 over square root of 2. There are just one roots. So you see that here we have minus plus minus, so we have to start by minus sign. Minus plus minus. Here we have f prime. And the behavior of f is decreasing, increasing, decreasing. Here normally we accept, we expect to have local minimum and here local maximum. It implies that f has local minimum at minus 1 over square root of 2 and then f has local maximum at 1 over square root of 2. I guess this part is easy because we had already this statement. We have just checked the behavior of the sign of f prime. Part 2. So we must check the limits at endpoints. Okay, here our AB numbers are minus infinity and plus infinity. You check limit x to infinity, x times e power minus x squared, which can be written as limit x to infinity x over e power x squared. So you now have an idea about this limit. This is of the form infinity over infinity form. So I can clearly use L'Hopital rule or L'Hospital rule. This implies limit x to infinity. If you apply L'Hopital, we have 1 over the derivative of x squared is 2x e power x squared, and whenever x approaches to infinity, we have 1 over infinity times infinity, we have infinity, so this is 0. Limit is 0. So this is my which number for this is my L. Again, limit x to minus infinity x over e power minus x squared. In that case, again we have so minus infinity over plus infinity. So again we have infinity over infinity form. L'Hopital gives the same result. Limit x to minus infinity. It doesn't change anything. 1 over minus. So maybe here we have I have a mistake here. This is plus because we have written it in the denominator. 2x times e power x squared. Again we have 0. This is my m number. Now remember, both L and M numbers are equal to 0 from left and right side of the given open interval. So now I'm checking if there is any number between L and M such that do we have a greater number than 0. Okay, compare L M with f of minus 1 over square root of 2 f of 1 over square root of 2. So you understand that this is the limit of f at the right side, this is the limit of f at the left side, L and M respectively, and you must check if one of them is greater than 0. So then we have f of minus 1 over square root of 2 gives us minus 1 over square root of 2 times e power minus 1 over 2, which is smaller than 0 indeed, and this is L and M. And moreover, f of 1 over square root of 2, this gives us 1 over square root of 2 times e power minus 1 over 2. Again, this is 1 over square root of 2 square root of e, or 1 over 2e. This is greater than 0, L and M. You can now observe from these two facts that so thus f has an absolute minimum value at x is equal to minus 1 over square root of 2, and its value, and it is equal to, and it is equal to minimum. So we are talking about the first one, 1 over square root of 2e. So let me state here, we can write it as 1 over minus 1 over 2e, smaller than 0. And f has an absolute maximum value at x is equal to 1 over square root of 2, and its value, it is equal to 1 over square root of 2e. We can show it in the following graph. Still we are not in the sketching part, but you can understand what I mean by this graph. Let me draw the following graph to understand how we can have this maximum and minimum values. Indeed, the graph at point at somewhere here we have minus 1 over 2e, here we have 1 over 2e, and the graph is minus infinity, but it comes here. Whenever it is here, it has a behavior on the following way, then it goes up to that point, then it decreases. And obviously you see that here and that one, here we have an absolute max, and here we have absolute min. So for today, for that lecture, this is enough for us. We can stop at that point, and for the next chapter, chapter 4.5, we will continue again.